Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we'll be talking about biomedical engineering and how it encompasses some of the most exciting new frontiers in both medicine and technology. My guest today is Dr. David Stout. Dr. Stout is an Assistant Professor of Mechanical and Aerospace Engineering. He also holds a Ph.D. in Biomedical Engineering. Welcome, David, and thank you for joining us on Talking Points.
Thank you for having me. I'm very grateful to be here.
Well, the first thing we have to do is reconcile this notion that you have a Ph.D. in biomedical engineering, but yet you're teaching aerospace engineering. So how do those two disciplines come together, and how can they actually complement one another?
That's a great question, and a lot of people don't realize that a lot of the engineering disciplines actually synergize to help with the biomedical field. For example, when I first started doing research, I looked at how fluid moves, what we call fluid mechanics. And this is really important to understand how airplanes fly or even how to build pipes underground for the water, say for toilets. And those equations that we use, we can actually use those same equations to understand how the circulatory system works or how blood moves through your body. And so we use the same equations and the same approaches. We just apply it, say, instead of a material or an airplane or a car, we just apply it to the body to begin to understand how the body actually functions and works.
So a mechanical engineer that wants to transition into biomedical applications and research, what kinds of additional training in medical science do they need to have?
That's another great question. What's great about being an engineer is you understand a lot of the really complex math and you learn about a lot of the really technical theories. To move more into the medical field, the medical transition, namely biomedical engineering, you as an individual needs to really focus on understanding biology and chemistry concepts. This might be a little difficult for an engineer to think because an engineer, we think in concrete terms. An equation is an equation. An airplane is an airplane, a material is a material. But in biology, it's not so concrete. It's very fluid. If you look at the research in biology, it kind of goes left and right, and we try to guess or check our ways. And so if an engineer wants to go to the biomedical world, first realize that it's not so concrete, but then second, really focus on and really begin to understand how the body works. So biology, chemistry, physiology.
So it all comes together, and that's the beauty of, I guess, biomedical engineering is the fact that it brings together all of these different disciplines into a practice that will help mankind solve some sort of medical problem or to develop therapies. I can think of an example historically, the polio virus, which was a major problem in this country in the early part of the 20th century. And so a couple of engineers at Harvard actually developed the iron lung back as early as 1927 to deal with the polio virus for people that had paralysis of the lungs. And so this was what we used. It was the big application, the big device. And in the 1950s, the polio virus reached actually a crisis level. In 1952, there were over 50,000 cases of polio where people had contracted the virus. Over 3,000 died. Another 22,000 or so were paralyzed and needed this kind of treatment. So along came Dr. Jonas Salk and others who developed the polio vaccine. So now we went from the big application, which was the iron lung chamber, to the microscopic, which was the vaccine. So now you just take a needle, stick it in your arm, and you're done with polio. So that's how we went from the big to the small, and we integrated all of those applications. Today we're talking about nanotechnology, which we'll get into in a moment, but we still have the big applications such as the MRI chambers and the CAT scan devices and so on, and prosthetic limbs. I know prosthetic limbs have really come a long way. Tell us about the latest developments in prosthetic limbs.
Yes, so there's actually a lot of awesome, innovative, and synergistic approaches that are using prosthetic limbs. The iron lung is a great example. And if we correlate that to, say, the prosthetic limb, When we first started prosthetic limbs in the 70s and 80s, it was just a metal rod. So if an individual had an arm that was amputated, you just usually had a metal rod or some plastic that a clinician or a doctor would put on that arm. And they would kind of put some rubber or some glove over it to make it look somewhat normal for the individual. But everybody noticed that, of course, it was a prosthetic limb. But what's really interesting is that prosthetic limb really didn't have the applications as, say, a normal arm. And a lot of the research now, again going kind of back to biomedical engineering, is you have a mechanical engineer that understands the material application. So we're looking at metals and polymers and plastics. We have an electrical engineer that understands the processes or how to make current move. And then what's really cool is now you have a neuroscientist or a neuroengineer where they understand how the electrical currents or the synapses of your brain function to get, say, I want to open or close my arm, to actually having the prosthetic limb open or close. So there's a lot of research right now where instead of having just a metal rod with a plastic over it or a rubber arm over it, you have this arm that actually functions like what a normal arm would do. So you could think, saying, I want to pick up a Coke bottle, or you want to actually grab a fork, you could think about it. All of those engineers and scientists come together to understand how that process goes from the brain now to the arm. You can pick up that, you can use that fork or pick up that Coke bottle and actually drink it. And so again, it's going from big and then going really small to actually saying, all right, we can help the individual by bringing all of these researches together to actually make something that people can use.
And in the 1980s, they made television programs about the bionic man, and
yes.
now it's actually coming true.
Oh yeah, there's a lot of bionic people now, right? Sometimes you might not even know that an individual might not even have, or might even have a prosthetic limb, and you have no idea because they walk normally, they can pick up a Coke bottle, they can even move their, they can move their arms, they can play baseball, they can play football, they can do a lot of these things that, as you said, in the 80s and 70s, that we might not be able to have done without the synergistic approach.
Exactly, and so now the latest frontiers are, of course, in the nanobiotechnology, and we're going to define that term, the nanoscale. Nano means 1/1000th of a meter if we're talking a nanometer, and that's how we measure these things. Mm-hmm. So 1/1000th of a meter, that means that if you take a typical hair, human hair, and you look at the cross-section or the diameter of that hair, you could fit 80,000 of these nanometer devices, if it's a single nanometer, on the tip of that hair. Some of the devices you've worked with are extremely small. What's some of the scale of things that you've worked on?
So a lot of the research that I have conducted and I still conduct, I'm talking about 10 to 15 nanometers, which again is, you say 80,000 per 1 nanometer. You can now say on the tip of that hair, you can, instead of putting 80,000, you can now put around 40 or even 30,000. So we're talking extremely, extremely small molecules. Not as small as a nanometer, but a little bit bigger, where we can actually add a couple things and work with them.
So we're working at the molecular level now.
A little bit smaller, but yes.
A little bit smaller? Okay.
A little bit smaller than molecular level, yes.
Okay, and I understand a hydrogen atom is about 1/10 of a nanometer or something like that, and
yes.
so we're approaching that.
Oh yes, definitely, yes.
Okay, and as far as how this can help us in developing treatments, we know that they've already developed man-made blood cells, red blood cells, which are called erythrocytes, and these are actually more efficient oftentimes than the erythrocytes, which are the naturally occurring red blood cells, mm-hmm. and so we can actually deliver, I guess, oxygenated blood throughout the body more efficiently with these man-made cells. Why is that helpful?
That's another great question, and we're not really, kind of saying replacing Mother Nature, but there's a lot of situations and there's a lot of individuals that have clinical problems with their body. For example, an individual, let's say, that is hemophiliac, where they always need blood, but also an individual that is in a car accident. You always need oxygen to regenerate tissue and to, heal an individual. And so if we can find a way to actually have faster regeneration of tissue, then we can help that individual continue, say, on their normal life cycle. Now, Mother Nature has done a wonderful job of making, red blood cells and all these other things. But what's really cool now, and in biomedical engineering is we're finally beginning to understand how Mother Nature works. And once we begin to understand, then we're like, okay, well maybe we can assist Mother Nature. If we can assist Mother Nature, we can help progress an individual that, say, is in a car wreck to regenerate tissue and to become back normal a lot faster than an individual that doesn't.
What you're really saying is that what we're doing with this nanotechnology is we're assisting Mother Nature to do better what she intended to do in the first place.
Yes, yeah. We're not replacing her, we're just assisting her, but the more, governing thing that we're doing is we're trying to really begin to understand her.
Right. Okay, and as far as delivery systems are concerned, these nano devices, nanoscale devices and nano particles can actually travel through the body. They can locate an area that needs to be photographed and photograph it, essentially. Mm-hmm. They can also deliver a chemical or a pharmaceutical application to that area, and the entire time they're doing it, they can be tracked externally by a scientist or doctor. And how can they track these things externally?
There's multiple different ways. One way that a lot of research has been going is using magnets. So for example, if you put a particle in an individual that is magnetized, you can actually take an external magnet that's outside the body and actually move it along your arm or even move it within the body. And so now you can see where it's going, you can actually direct it to the location you want to. Another way is using photonics or light. And so with light, we can, if we heat it up, certain things can glow when they heat up. And so now we can actually track them by using photos or even light. So we can say, all right, well, here's the particle, and we know where it is. And we can actually do it electrically as well. We can have a particle that's electrically conductive, and if we just shoot, I say, a little bit of electricity through an individual, then we can say, all right, well, there's that particle because we know where it is. And so again, it's going from this really big to this really small. Instead of sticking someone in a huge MRI scanner, we can just say, have a little magnet that we can place on an individual, or even take a picture of an individual and say, all right, that's where they are. So it's less invasive is what we're really trying to get at.
We just have a couple minutes left, but I want to talk about one of the new innovations that has the scientific community pretty excited, and that is an application known as electronic aspirin. Yeah. So that for the sufferers of migraine headaches, oftentimes what causes the migraine is nerves in the sphenopalatine ganglion, which is this nerve bundle in the face, mm-hmm. and something goes awry and a neurotransmitter sends out pain signals. And with this new process, they can insert a particle in there, and the patient can actually take a remote control device, hit the button, and it stimulates that particle, which gets the nerves going, mm-hmm. which then block the pain signals from those neurotransmitters. Is this sort of similar to, and the next iteration up from, a pacemaker that had been installed to regulate heartbeat?
Yes, and that's a great example as a pacemaker as well as this new innovation. Whereas we look at the pacemakers in previous time, it was always a monitoring system where an individual always had to monitor themselves. And now, or a doctor had to monitor themselves. Now we're taking not really the doctor out of it, but allowing the individual to take control of their body. For this great example of using this little particle and an individual feels like they're having a migraine, they just kind of click a button and they say, all right, I know I'm having a migraine, now I can assist my body and I know how my body feels. Now the next generation, which is even great, is actually getting that individual out and creating particles or even systems where we can look at pathways or chemicals that are released in the body, and we can actually tell the machine, all right, now we want to release this chemical or even this drug, so the individual doesn't even have to think about having a migraine, or the individual doesn't have to think, all right, well, I'm feeling really bad, maybe I should give myself an extra pump of, say, insulin, or maybe I should drug myself a little bit, not really drug myself, but release some drug chemicals so that I don't have to, so I don't have to have, say, a migraine.
We're going to have to go to a break right now, and we'll continue this conversation in a moment. And please stay with us. We will continue this conversation about the exciting new frontiers in biotechnology in just a moment. Stay with us.
Hi, I'm Jane Close-Connolly, President of Cal State Long Beach. Thanks for watching Beach TV.
There are some jobs that are just plain fun. You can be a park ranger, working to preserve our national parks. Or maybe an adventure travel coordinator, organizing all kinds of adventure tours. Or maybe you want to work in the community and work as a Parks and Rec director. The opportunities are endless with a degree from Cal State Long Beach.
Hello and welcome back to Talking Points. I'm Dave Kelly. My guest today is Dr. David Stout. We're talking about the exciting new frontiers in biomedical engineering. And David, before we went to the break, we were talking about a number of items, particularly things like electronic aspirin, nanoparticles that we can insert into nerves and into various parts of the body for therapeutic purposes. I want to get into something which is definitely a new frontier, and some would call it a brave new world in a negative context. So we're going to try to work through this and see if we can come to some resolution on that issue. And that is, in terms of having children, we now have technologies that can assist us in having a healthy baby, whereas it might have been a roll of the dice before. And I'm thinking of a new development called three-person babies, so that you have the father and the mother, and you have a second mother providing a donor cell. And what happens is the fertilized embryo comes from the mother, but she has a mitochondrial disorder, so that that will be carried on and passed down to the infant, and we want to avoid that. So we take the DNA, which is the nucleus of her fertilized embryo, extract that, and then we discard the rest of that cell, and then we take a donor cell where we take out the nucleus, but it has healthy mitochondria. We insert the healthy nucleus from the mother into the donor cell, then we have a three-person baby. So the question is, from an ethical standpoint, is this playing God? Are we crossing a line in what's referred to as eugenics by doing this? Or is this back to what we talked about in the first segment about knowing what Mother Nature intended and just helping Mother Nature do what she had intended all along, but removing any barriers or obstacles to that process? Your thoughts?
That's a great question, and from a scientific perspective, I usually am definitely on the road of kind of assisting Mother Nature, which we talked about previously. My job really is to begin to try to understand how Mother Nature works. And when we understand how Mother Nature works, we can, as you said, get rid of those roadblocks. And when we get rid of those roadblocks, we can then, help people have, say, a better life or a healthier life. I am not a parent myself, but when that time does come, if I had an opportunity where I'm pretty sure I'd love my child if they had a medical defect or not a medical defect. But if there was an opportunity where, because of modern research came to play and said, well, we did these tests and we found out that your individual might have this medical defect, do you want to proceed, or would you like an assistance from science to help and make sure the individual is not born with that medical defect? I'm pretty sure that I would most definitely probably go towards the route of having that individual not born with that defect, not because of my selfish perspective, but because I want my individual or my future child to have a healthy, happy, most fulfilling life. And so I feel like it's not really playing God, but again, helping Mother Nature understand to do what she intended to do.
So we're, again, just to reemphasize, you don't see that as supplanting Mother Nature, but rather assisting Mother Nature, being her handmaiden.
Yes, being her handmaiden. Everybody needs help in this life, and scientists, we feel like we're trying to help Mother Nature.
Okay, let's talk about DNA, since we brought that up with that example. Extracting DNA from a cell has been difficult in the past because the DNA is very delicate, and when you go in to extract the DNA, depending upon how it's done, if there's a lot of turbulence, there's some enzymatic issues that can develop, and the enzymes can flare up and actually destroy the DNA. Or you can have a mechanical problem of trying to lift it out, and then it tears in half, or it shears apart, or something of that order. But with new nanoparticles, we can actually get down to such a microscopic, tiny level that this isn't a problem. How does that work?
That's another great question. And what's really cool is because nanoparticles are so small, they can actually diffuse or move along the cell's body very easily without really affecting how the cell works. So it can go through the cell wall, it can go into the nucleus, and then it can actually go and what's really interesting is penetrate the DNA. And so what we're doing and what we're building is a device or a system that really goes in and tries to assist or even diagnose the cell or say some form of abnormality in the cell without really affecting its natural environment. So the old days of shearing and ripping cells in half and doing all this crazy stuff just to try to get to the DNA, we're trying to move away from doing that, and where we just take these little nanoparticles, they move along the cell, they find the DNA, and now we can use medical devices to say, heat up the nanoparticle so we can fluoresce, so we can image the cell, and we can begin to understand really how DNA works in its natural environment.
So we're able to embed the nanoparticle into the actual DNA.
Yes, that's a very, very good question. Well, not really a question, but a really good statement, is that we can even embed particles into DNA or even kind of rip apart DNA itself.
Okay, let's move on to another area that's related to that, and when you get to that nanoscale level in cells, you're going to run into what are known as viral vectors. And viral vectors can go either way. They have properties that we all know that viruses can be very negative. We talked about the polio virus, and we certainly know that they vector because they do spread. But we can also take advantage of some of the delivery systems or distribution systems that the viral vectors provide. Explain that. What is a viral vector exactly, and why do we have to be concerned about it, and how can we use it to our advantage?
So, in a simple sense, a viral vector is a way that a virus, or the ability of a virus to be able to multiply in a very, very fast way. And say that we have a particle or a drug delivery system that can actually attach to that viral vector. Now we can take that particle or say a drug, and we can kind of change it a little bit, and we can take the advancements in viruses of be able to produce really fast and move really fast and go to particular locations very, very easily and use it to our advantage where, let's say that we can dehorn or get rid of that negative part of that virus, but use the advantage of moving the virus through the body to get to a particular location really fast.
Right, I think they use the term pseudotyping with the viral vector, so that we've defanged it, as you were saying, so that it has all the properties of movement without the negative effects of infecting a cell in a bad way.
Yes.
Okay, so as we talk about that kind of thing, you know, there's cancer treatment today. There have been a lot of new developments in cancer treatment, where in the old days we started with, let's say in the 1950s, if you were diagnosed with cancer, about all they could do for you was surgery, remove a tumor once the tumor was identified, and then, but there could also be malignant cells still in the body that they didn't catch. So then we developed chemotherapy to take care of those traveling, migrating malignant cells. But chemotherapy is very harsh, and it has a lot of toxicity to it, so it destroys a lot of healthy cells at the same time. So then we developed targeted radiation to radiate that area, hopefully not spreading to the rest of the body if we can do that. And then finally we got into the Genome Project, DNA, and we learned more about how cancer cells attach themselves and create proteins and things of that nature and replication. So now we're in the nanobiotechnology, where we can actually play a kind of, the analogy would be cat and mouse, where we have the mouse, which is the malignant cell that wants to reproduce. We know that mice like to reproduce rapidly, so those malignant cells are traveling and trying to attach themselves to various organs to create tumors. But the cat, in this analogy, is the chemical that's brought in by the nanoparticle. So the nanoparticle is trying to chase through the body to find the place where that mouse is going to nest and stop it in advance. Pretty exciting, I would say.
Oh, it's definitely exciting. And going back from one of our original examples that you talked about going from really big to really small, what we're seeing in cancer is really evasive to something that's really non-evasive. And what you talk about is amazing. You just take this shot with these nanoparticles that have chemicals that are attached to them, where they can kind of embed a cat into looking for these particular cancer cells. So again, going very invasive to non-invasive. And what's even cooler is once that we find these special chemicals and these special proteins, where we can really hone in on where we know or where we might be able to find out where that cancer is going, we can then create nanoparticles to say, all right, go to this specific location, and we know that cancer is going to be there, and so kill it before it grows and metastasizes. So again, from very invasive to just a shot.
Right, and there's another development that's coming along, which is called senolysis, which is where you have what I refer to as these microbubbles that are filled with some kind of chemical or gas or what have you, and they travel through the body, and they can be used to, address a blockage of a vascular area, a vein blockage, or also they can explode and have what I consider to be exploding dye, where the bubbles pop and this chemical that can be, seen photostatically or through thermal censoring or something, so that they can operate in that way. What do you know about senolysis at this point?
Well, it has definitely progressed. And again, going back to the idea of becoming very invasive and non-invasive, is the senolysis perspective of where they can blow up and they can target. What helps is, instead of going where, for example, you have to put a spring in a vasculature or a stent that a lot of people know about, now we have these little particles, these little bubbles that can directly go to that location, sense what's happening, and then get rid of the problem before it becomes a major occurrence.
David, I want to thank you for being here today. We've actually run out of time. There's a lot more we could talk about. We just can't do it right now. But thank you again for being here, and good luck with all of your research and your teaching.
Well, thank you, and thank you for letting me talk about the amazing research that's happening in biomedical engineering.
And thank you for joining us on Talking Points. Join us again soon for another episode. Until then, I'm Dave Kelly. Have a nice day.